thank you for introduction. I'm grateful to the organizers for giving me this opportunity. Today's talk is joint work with Toshino. He's there. Unfortunately, our preprint is still in preparation, but you can read this QR code to access today's slide. The QR code will be shown again at the end of the talk. Today's main topic is a generalization of accessible and local presentability. So let's start with the ordinary one. Before that, the co-completion under filtered coordinates is called within the completion. And it is constructed as the filtered coordinates of representable. Besides, a finitely presentable object is an object whose confunctors preserve filtered coordinates. Using finitely presentable objects, we can characterize the inner conditions. In fact, a category X is equivalent to the inner condition of some category if and only if X has filtered coordinates and every object is a filtered coordinate of finitely presentable objects. Then, if we ignore the size matter, this gives a definition of finitely accessible category. Furthermore, we can tell this story not only about filtered coordinates, but also an arbitrary class of coordinates. Indeed, if we are given a class 5 sets of coordinates, the free co-completion under 5 coordinates is also provided by 5 coordinates of representables. We will call it the phi inner completion today. We can also define phi atomic objects corresponding to finitely presentable objects. This is also introduced this morning. But then, this gives a characterization of phi inner completion and a definition of phi accessible categories. Okay. And now, I introduce a motivating duality theorem in this context. Let phi be a nice class of shapes of coordinates. In the duality, this kind of functor plays an important role. A functor such that a left-hand extension along it computed as 5 coordinates. However, I don't know what this is called. So for now, I will call it a phi-weighting functor. Then, here is a motivating duality theorem. There is a bivalence of 2 categories. The left one consists of Cauchy complete small categories and phi-weighting functors. The right one consists of phi accessible categories and phi co-continuous right adjoint functors. This duality is a phi-modified version of Mackay-Paré duality. The same kind of this in the locally presentable context is just called Gabriel-Ullmann duality. Note that this kind of duality has recently been generalized to enriched context. I will not describe the enriched accessibility in detail, but it is much the same as set and case. Now, I will explain today's strategy. The theory of re-enriched accessibility, for example, duality, intercompletion, and Cauchy completeness, can be regarded as the accessibility in Bitcoin. here, B prof is like a universe for BM category theory. This consists of BM categories and B functors and B profunctors. For experts, B prof is a virtual equipment, which is a special kind of double category. Today, we will generalize the universe from B prof to arbitrary virtual equipment. And this is today's goal, and this will extend the notion of accessibility to other category theoretic contexts, such as bi-category image categories, fiber categories, internal categories, and something that is no longer category. For clarity, let me explain why we use virtual equipments. Classically, two categories are also regarded as universes of category theory. Indeed, two categories are suitable for capturing several concepts of category theory, such as ordinary limits and colimits, junctions, monads, and Kant extension and limits. However, they are not suitable for capturing interactions of functors and profunctors. This includes weighted limits and colimits, shields, completions, and so on. On the other hand, virtual equipments are one of the suitable frameworks for these concepts. This is why we use virtual equipments rather than two categories. Before I get into the detail, let me explain the main features of our framework. In our formalization, we don't use opposite categories. This means we can treat categories imaged over a non-symmetric model category or a bi-category. Next, we require neither the smallness of categories nor the compositions of profunctors. This bypasses the size matters lying in free completion. Furthermore, we don't demand co-completeness for the universe. This allows us to treat enrichment by a model category that is neither co-complete nor closed. In the next part, I will quickly explain what virtual equipments are for people not familiar with double categories. As already explained, B prof is a universe of the category theory. It is a double category. More precisely, it is an augmented virtual double category for experts. B prof consists of not necessarily small B categories, and the functors and their compositions and identities, and D profunctors. The word virtual means that we don't consider their composition.
How can you define profunctors without using the Q and the opposite? How can you define profunctors without using opposite categories?
Yes, we consider profunctors as something like module. Makes sense. In addition, B prof has generalized B natural transformations called B forms. Each B forms has its RP, which consists of two B functors, F and G, and finally many B profunctors, P1, P2, Pn, and Q. The word augmented means that we actually consider another type of form like this. Here, the profunctor Q is replaced by the home profunctor of B. Moreover, this B form can be composed like this. If we are given finitely many B forms alpha and beta, then we can obtain a new cell, and we can obtain U1. By the way, if you look closely, you will find two types of horizontal arrows on this slide. Dashed one and dotted one. For convenience, we let a dashed arrow denote a finite couple of arrows, and let dotted one denote a finite couple of arrows of length 1 or 0. Considering B prof as a typical example, we can understand general augmented virtual double categories. Here, B categories are replaced with objects, B functors with vertical arrows, B profunctors with horizontal arrows, and B forms are replaced with cells. Then we can define virtual equipments as special augmented virtual double category. A virtual equipment is an augmented virtual double category such that for every data like this, there exists a canonical horizontal arrow P and a cell. This cell is called a Cartesian cell. Cartesian cells are defined by a suitable double categorical universal property. Here are example of virtual equipments. Of course, B prof becomes a virtual equipment. A monoidal category B can be replaced with a bicategory W. And there is a virtual equipment for eternal category, and so on. The important thing is that a virtual equipment plays a role as a universal category theory. From now on, we will fix an arbitrary virtual equipment E, and we will do category theory in it. Okay, in the next part, I will briefly explain how we do category theory in a virtual equipment. In a virtual equipment, we can define many types of cells by several universal properties. Those cells play a crucial role. For example, if we are given a path of horizontal arrows like this, then we can consider a universal cell of this form. This is called a composite cell. For experts, this is also known as a strongly Cartesian cell. Here, the emphasis by red color indicates that it is uniquely determined by a universal property. When the path has length 0, opposing cell takes this form. In the virtual equipment B prof, opposing cells can deal with composition of profunctors and limits in B. Next, if we are given data like this, then we can consider a lifting cell of this form. And its horizontal viewer is called an extending cell. In B prof, these cells can deal with lifts and extension of cofactors and limit in V. Next, if we are given data like this, we can consider a right can extension cell, or simply a round cell. So for example, there is a left can extension cell. These cells can deal with weighted limits and coordinates, and point-wise can extensions. Now, many types of cells have been introduced. Cartesian cells, composite cells, and so on. They are closely linked by several important lemmas and concepts. For example, there is an important lemma called sandwich lemma that connects between composite cells and Cartesian cells. I think formal category theory in virtual equipment is a puzzle to be solved using these relationships. This is our story. Next is the last part. We will double categorically formalize intercompletions and duality theorem introduced at the beginning. First of all, we consider how co-completeness and co-continuity are treated in a virtual equipment. For today, we will distinguish between weights for limits and weights for points. And we call them left weights and right weights, respectively. In a virtual equipment, a left weight is simply a horizontal arrow. Given a left weight phi from A, we will regard A as the shape of diagram and phi as weights parameterized by B. Then we can consider co-completeness in a virtual equipment. Let phi be a class of left weights. Then phi co-complete objects are defined by the existence of round cells like this. Here, canonical arrow from B to X is regarded as the phi-weighted coordinates of phi-weighted coordinates of M. Furthermore, phi co-continuity is defined by the preservation of such round cells. In summary, a class phi of left weights plays a role as a class of shapes of coordinates. Next, to formalize intercompletion in a virtual equipment, let's begin with observation in deep. Recall that the phi intercompletion is given by the phi point closure over in zeta mode. However, if the class phi satisfies a nice property, it is also given by all the precisions in phi, like this. Then, which is that a functor in the A corresponds to a profunctor whose restriction by B belongs to phi. In the previous part, I described that the codomain of profunctors plays a role as a parameter. So this profunctor will just be regarded as profunctor belonging to phi. This corresponding leads us to an abstract definition of the incompletions. Given a nice class of left weights phi, we can define a phi endomorphism by adjoint equivalencies like this. The left side is the category of vertical arrows, and the right side is category of phi weights. This concept directly generalize the construction of phi in the competition in Kyoto. And note that phi endomorphisms are a phi modified version of Yoneda morphisms in the sense of Kudeberg. From now on, we will write phi A as codomain of a phi endomorphism from A. Since phi A is unique up to vertical equivalence, this notation makes sense. Then, several natural questions could be considered. The assignment phi is a factor, and what should be the codomain and the domain of phi? And does phi have a universal property? To answer this question, let us start with a few observations. First, by definition, we have a bijective correspondence between phi weight and vertical arrow to phi A. Moreover, there is another correspondence as a phi co-completion. If an object B is phi co-complete, vertical arrow corresponds to a phi co-continuous vertical arrow from phi A. One can prove this directly from the definition of phi endomorphism. Then, if we consider a projective factor U, phi would look like a left adjoint with respect to both horizontal arrows and vertical direct arrows. Indeed, it is true if we prepare phi's domain and codomain double categories as follows. The domain double category E phi is defined by restricting the horizontal arrows to phi. The codomain double category Q phi is obtained by the quintet-like construction. Objects and vertical arrows are restricted to phi co-complete and phi co-continuous ones. Horizontal arrows are vertical arrows in opposite direction. Then we can present phi as a left adjoint of U. To be precise, these data form a relative adjunction because phi can only send objects whose phi in the competition exists. More precisely, they are bi-adjunct. This is because that phi only has a weak functoriality. It should be emphasized that they behave like a relative bi-adjunction with respect to both vertical and horizontal directions. We call such data a relative company bi-adjunction, which will be a new concept. Unfortunately, its complete definition is so complicated that I can't explain it here. So it is omitted today. Then, such relative company bi-adjunction brings us desired duality story. This is today's main theorem. Restricting to phi, we obtain an equivalence of double categories. The left double categories consist of closely complete objects, and this consists of phi-weighted vertical arrows and phi weights. The right double categories consist of objects in image of phi. Phi co-continuous like adjoint, and phi co-continuous vertical arrow in opposite direction. The object in the right double category is called phi accessible object. Now, we have generalized the duality theorem to the double categorical point. Before we finish the talk, I will mention our ongoing work. In today's talk, we only dealt with accessible context. So, developing a formal theory of locally presentable objects is still ongoing. Next, we are short of examples. We have to explore virtual equipments that provide us with interesting duality. For example, the virtual equipment for fiber category theory, length category theory, and so on. And we should also compare our framework with related one. Formal accessibility in a two category. Now, my presentation is finished. Thank you.
Thank you. Other questions or comments? Okay.
Can you actionize equipment that admit these incompletions? Like, is there some actions that equipment should satisfy for these incompletions to exist?
No, we don't assume the equipment any condition.
There is hope. Yes.
Can you say something about what you mean by phi being nice?
Sorry?
By the class being a nice class of weights?
You asking a precise definition of
Well, just
nice
like in your context, what it looks
okay,
like.
there is extra slides. It's here. Nice means a class is the left doctrine like this. I think this corresponds to saturated class.
Okay.
There was another question.
Your virtual equipments, do they have horizontal units? How is it clear to you?
Yes, in this work, we consider the horizontal unit. So it is not essentially augment vertical pattern, but for future work, we use augmented vertical pattern.
In your talk, I think it was slide 15, you showed this big triangle of different properties that can be expressed in virtual equipment. Yes, this one. Are there nodes that you can add to this graph that of properties that can be expressed? Are there examples that you haven't included in this picture?
Time is up.
It's all right. Could you tell me
Yes.
later?
Yes.
Thank you again.